All right, so we're going to talk about the difference between exponential growth and exponential decay. We're going to practice writing some equations. We're going to get up to doing some solving stuff today, working with all kinds of pieces. I'll talk about that at the end. No, it's not. Yes, we're not there yet. We're not ready for it. Okay. So when we're looking at these exponential functions, that's when we're thinking about our kind of basic form, a times b to the x. Maybe plus k, maybe not plus k. Sometimes there's a k, sometimes there's not, so we just go with it. Exponential growth is when we have a graph that looks kind of like this. And when that's going to happen for us is if we have an a value that's positive. So we're just going to start by thinking about with a being greater than 0, it's positive. What that's going to mean is if our base is bigger than 1, we are going to have exponential growth, meaning our base is something like 1.5 or 2 or 3. It's getting bigger as we go, so it is growing. Exponential decay is very, very similar. If we again think about our a value being positive, so with a positive a value, exponential decay kind of looks like this guy. So with a positive a value, our base needs to be less than 1, but it also can't be negative. So it's going to wind up being between 0 and 1. I don't like the plus on the a, so with positive a. It just looked weird, so I'm just saying with a positive a. You can word it whatever way you want. My plus looked weird. So that would mean our b value is small. It is getting smaller and smaller and smaller as it goes. If we have a negative a value, what that's going to wind up doing is it's going to take the b's and switching them, because it will do that reflection across our x-axis. So we're going to practice with it later, and we'll see what that looks like a little bit. What we're going to be starting to look at is trying to take either graphs or sketches and see if we can figure out where the equation is coming from. And so we're going to be looking at the a, the b, and the k and how they interact with each other. When we're looking at these kinds of equations, we are pretty much always going to be given our y-intercept. And where the y-intercept is really helpful is it can help us figure out what a is going to be, because what the a value is in the equation is the distance to our asymptote. So if it has an asymptote, we have to include that in here. But we can find a, if our asymptote is 0, it is just going to be our y-intercept. Or we can do our y-intercept is a plus k. It is the difference between our asymptote and our y-intercept. When we're trying to figure out our base, we are almost always going to be given another point. So whether it is another point that is a little farther away or another point that's right next to it, we're going to be given some more information, and we can use that to help us find our values. So our y-intercept is going to be the distance from our y-intercept. Yes, distance from our y-intercept to the asymptote is going to be the a value. So if the asymptote is 0, it just is a. Otherwise, we have to find it. With these exponential growth functions, something that's going to come up for us in just a couple of days is, since we have exponential growth, it is always increasing, which means this is a one-to-one function, and we will be able to find an inverse for it. It is always increasing, no matter which direction it's going, if it's exponential growth. Exponential decay is always decreasing. which means, again, it's 1 to 1. So we're going to be able to find the inverse of them. And we will get to the inverses of the exponential functions before the end of the chapter. We'll get there. Okay. So we're going to use some of this information to take a graph and write an equation, and to take kind of a description of a graph and write an equation. And naturally, since we're going to be looking at a graph, I printed it for you, so you don't have to try and speed sketch it. So I'm going to pass these out. I have several things that we're going to have options to glue into the notebook, or into your notebook for you. They just all kind of printed out in a very chaotic order, so it's like all cut apart already halfway. So again, if you don't use these, it doesn't matter anyway, so it's okay. But you guys have it as an option. So these are just graphs. We're going to look at them, and we're going to try and write a whole equation for this graph. We want to try and figure out the whole document thing. So we're going to look at these two here. And that first one is the graph you guys just got. Sure. And we're going to try and write these in the form our y equals a times b to the x plus k. So when we're looking at pictures like this, first thing I want to start with is, do we have an asymptote? Yes. That's this dotted line right here. We have an asymptote. That is going to be k. K is the y value of that asymptote, so our k is going to be 1 here. The way we can get a, we have two different options for it. We can figure out how far our y-intercept is from the asymptote. I can look at it that way. Or we can do that our, I don't know why I put a equals. Eraser. A plus k equals that y-intercept. Well, I already know k. K is going to be that 1. So a plus 1 equals our y-intercept. Bless you. Our y-intercept here is going to be 5. We're told that one. That's right there. So what is our a going to be? 4. It is 4 steps away from our asymptote, or the difference between our asymptote and our y-intercept is 4. So it has been started right there. So we took our a plus k, and we already knew what k was, and we can find our y-intercept from the picture. So at this point, just from this alone, I know lots of pieces of my equation. I know that my y is going to equal 4 times some base to the x plus k plus 1. And I need to figure out what b is, because I don't want to have 3 letters left. I want to have 2. I'm okay having an x and a y, but I need everything else filled in. We are given another point here. I'm given 1, 7 is also on our function. 1, 7. So we're going to substitute those in. My y is 7. I know my a is 4. Trying to figure out that b. My x is 1 plus 1. And we can solve this, because I can subtract 1 from both sides. Just changing my color. There we go. Oh, so we'd have 6 equals 4 times b to the first, which is just b. So what is b going to equal? What is our base? Careful, not 3/4. 3/2. So either 6/4, excuse me, 6/4 or 3/2. So we can use the information about these relationships to take just a sketch or a picture and find our whole equation. Because our whole equation here is going to be our y equals 4 times our 3/2 to the x plus 1. So k is always going to be our asymptote. Our y-intercept is the difference between our asymptote and the y-intercept. Or our a is the difference between our y-asymptote and our intercept. And our base is how much it's changing. We can substitute that in and solve for it. So start with your asymptote and then find your a and then find b. So the second one, it's not a picture. We can give ourselves a sketch if it helps, but we didn't, it's not like from a graph. So if it helps you, you can absolutely sketch this out. We know we've got a y-intercept at 8, and it's going to go through the point 3, 1. So this function is going to look like this. We've got an exponential decay here. They also straight up tell us there is no asymptote, or at least none shown. It's going to be at 0. So our k equals 0. There is no shift in the asymptote. So that means our a, the difference between our y-intercept and 0, where our asymptote is going to be 8. So if we do not have a shown asymptote, it's at 0. And our a will be the y-intercept. If we have an asymptote, we have to find the distance from our y-intercept to the asymptote. Otherwise, it's at 0, and it is just going to be a. So from that alone, we have a lot of the pieces. We have our y equals our 8 times some base to the x plus 0. We don't have to put the 0 on there. We can. If it helps you, put it there. If it doesn't, don't put it there. And we can go through this the exact same way that we did on the last one. Substitute in our x and y. That way we can solve for b. So we're given another point. We're given this 3, 1. So I know my y value is going to be 1 for 8 times whatever the heck our base is cubed. B to the 3rd. So if I divide both sides by 8, we're going to get our 1/8 equals b cubed. So what is our b going to be? The cube root of 1/8. What is the cube root of 1/8? 1/2. Cube root of 1 is 1. Cube root of 8 is 2. So our base here is 1/2. So our whole equation would be that y equals 8 times our 1/2 to the x. So it's a little awkward and it requires a little practice, especially when we have the asymptotes. They're a little weird. The calculations, we've done this kind of stuff before, but they're just super awkward. And especially when we have the asymptotes, it makes things really, really weird. Okay. Questions on those two? So we had here a growth because our base was bigger than 1, and a decay because our base is smaller than 1. So what we're going to do is I'm going to put up 6 examples of equations, and we are going to decide whether it is growth or decay. And there's a couple of them that are a little bit tricky, but for the most part, all we care is growth or decay. And so it would honestly take us longer to write these down by hand, so I printed them again. Again, you don't have to use these. They're there if you want them, but you don't have to. But, you know, just instead of us having speed right pace, I put them up. So we're going to look at these 6 and try and decide if they are exponential growth or exponential decay. So we don't have to do a lot of work on this. We just want to say, is it growth, is it decay? We might have to give ourselves a little bit more information to be able to tell that. There's a couple on here that are trying to trick you because they love to pull those out. First couple are fairly straightforward. So on this first one, top row, is this growth or decay? Growth. Our base here is bigger than 1, so this one is growth. It would look like this. You would have our starting at 1 times 2 times 2 times 2 times 2, and it's just going to get bigger and bigger and bigger. What about this second one, y equals 1/3 to the x? Is this growth or decay? Decay, because our base is smaller than 1. We cannot have bases that are negative. The base itself cannot be negative, because then it's not going to be continuous as a function. So decay kind of looks like this as we're getting it set up. I'm going to redraw that because I didn't like that curve. There we go. Decay kind of looks like this for our positive a values. What about this third one, 2 times 3 to the x? Growth. This guy right here is what we're looking at. 3 is bigger than 1, so this one is in fact growth. Bottom row. This one is decay. It is the 1/5 that makes that choice. It's smaller than 1, so that one is decay. Here's where they're going to start trying to trick you. We've got minus 2 to the x. I'm 100% with you that 2 to the x, like this is growth. This guy up here. What does a negative a value do? Flips it across the x-axis. So because we have an a value that's negative, it's been reflected. So now it's not pointing up like this guy. This has been reflected across the x-axis. It looks like this. So is it growth or decay? Decay. So if our a value is negative and it's causing us to have that vertical reflection, the reflection across the x-axis, then we're going to wind up with our b rules have to flip spots. Decay, it would be bigger than 1, and growth, it would be little bitty numbers, fractions. The last one is also trying to trick you. Because we have 7 to the power of minus x. We didn't have minus x as an option for that before. So what if we rewrite this as 7 to the minus 1 times x? Or I can do this as 7 to the minus 1 to the x. How could I rewrite 7 to the minus 1? 1/7. This is the same thing as 1/7 to the x. So is this growth or decay? Decay. So they will try and trick you sometimes. So make sure you're looking at the details. The details are important. Those signs are very important. So when in doubt, if you need to, give yourself a little sketch. Sketch out a little growth, sketch a decay. It doesn't have to be perfect. It doesn't have to be pretty. Sometimes a visual really helps. Okay? Questions on these ones? Because we're going to do a quick refresher of some of the things we saw in Algebra 2, and then we're going to do a couple of Precal version. Because we're going to work with solving exponential equations. We're going to, given 2 pieces, 2 exponential phrases set equal to each other. And we want to solve this. Solving meaning getting all the way down to an x equals. So the whole goal is to get down to x equals something. And now we did things like this in Algebra 2. How could I solve this? What do I need to do? Yeah, when we have this same base here, 5 to the something equals 5 to the something, I just need those two somethings to match. I need to know, when does 2x plus 11 equal 2 minus x? We can solve that. That's a linear statement. What do we need to do? Add x on both sides. 3x plus 11 equals 2. Subtract 11. 3x equals negative 9. And divide by 3. X equals negative 3. And you could check that if you want to by putting that in the calculator. 5 to the power of 2 times negative 3 plus 11. Well, 2 times negative 3 is negative 6 plus 11, 5. 2 minus negative 3 is 2 plus 3, 5. So 5 to the 5th equals 5 to the 5th. We don't even have to get all the way to what is 5 to the 5th, because that's going to be big. But 5 to the 5th does, in fact, equal 5 to the 5th. So you can substitute those x's back in to get a little check going, if that's helpful for you. So if we're handed the bases that are exactly the same, easy peasy, set your exponents equal, go from there. What about something on the right? Our 3 to the 5x minus 8 equals 9 to the x plus 2. We want to have them have the same base. So what can I do to make them have the same base? Rewrite 9 as 3 squared. I know the relationship between 9 and 3 squared. But I can't just square root, and I can't square the left-hand side without also squaring the right-hand side. But I can rewrite 9 as 3 squared. That means the same thing. I'm going to move that down a line just because that's really close. So I can rewrite my 9 as a 3 squared, everything else staying the same. So now I have powers raised to powers, and I'm really close to having the same base. What do I do when I have a power raised to a power here, between this 2 and the x plus 2? It's going to multiply 2 times the x plus 2. So this is the same thing as having our 3 to the 5x minus 8 equal 3 to the 2 times x plus 2. And now we have that same base. So at this point, we're only going to give you options that can be put as the same base. We just have to be really careful how we do that, because we want to know when these two exponents equal each other. We want to know when 5x minus 8 equals our 2 times x plus 2, also known as 2x plus 4. And we can solve that around. Subtracting 2 from both sides, we get our 3x. Adding 8 to both sides, we get 12. So what is our x? What do we get as our solution on that one? 4. And again, we could substitute that back in. Type in the calculator 3 to the 5 times 4 minus 8, 9 to the 4 plus 2. We will get the exact same number. You could substitute it back into check. We don't necessarily have to. We're not going to wind up with any like extraneous situation or extraneous solutions here, just because of the way exponentials work. But if we're not entirely sure, it's a great way to double check. Questions on these two? Just because it's been a minute since we solved one of these. Cool. Let's do it again. Here's 2 more of them. So we've got 9 to the 2x equals 27 to the x minus 1. And we have a relationship between our bases, but it's not as a power. Like, I know 9 times 3 gives me 27, but I can't do it as multiplication. What are we going to need to do? They're both going to wind up having a different base. We're going to have to change both bases to a 3. Yeah, because I can rewrite 9 as 3 squared, and I can rewrite 27 as 3 to the 3rd. So I can rewrite my 9 to the 2x as 3 squared to the 2x. And I can rewrite my 27 to the x minus 1 as 3 to the third to the x minus 1. So that gives us those same bases after we do this multiplication. So we're going to have our 3 to the 4x equals our 3 to the 3x minus 3. If you can skip down here, as long as we are accurate with it and we don't make mistakes in it, I'm totally cool with that. It's just one of those things that from here, sometimes we make the mistake with this multiplication here. And we forget to multiply times the whole factor. If you don't need to write this step, that's fine. But for a lot of us, this saves us from mistakes with signs, especially. But if you can go straight from here to just looking at our exponents, I totally get it. What is our answer going to be on this one? -3. It is possible to get a no solution. No solution does still happen. It's not super common, but it does happen every now and then. So that is a possibility. 0 is also a valid solution. That doesn't mean no solution. Remember that 0 is a valid number. We're going to get to do the very similar thing on this next one. 4 to the 2x minus 1 and 8 to the x. What base are we going to wind up using on these? 2. Because I can rewrite 4 as 2 squared to the 2x minus 1. And I can rewrite 8 as 2 cubed to the x. They should always be numbers that are fairly familiar. We're not going to ask you to do this with like 1,424. But if we know our perfect squares for sure through at least 10 and our perfect cubes through at least 5 or 6, that would be helpful. Just so that we have numbers that we can recognize. Like I don't think even the homework we even asked you to do more than that, higher than that. Just double check it. Cool. Because now we can look at just our exponents and we can get our 2 times 2x minus 1 set equal to our 3 times x. So that's giving us a 4x minus 2 equals 3x. What are we going to get as our solution for our x? And again, I could put that in, substitute that in and check. 4 to the power of 2 times 2 minus 1. Well, 2 times 2 is 4. So it's 4 to the third and 8 squared. 4 to the third is 64. 8 squared is 64. Absolutely works. Okay. We've worked with ones just like those before. Precal version. Very much the same vibe. Only difference here in these ones is we don't have just linear statements in our exponents. I've got x squared in the exponent. Powers within powers, holy powerception. It does not change the process. We have our 4 to the x squared plus 8 and our 64 to the 2x. I still want them to have that same base so that we can set our exponents equal to each other. So when we're looking at this first one here, our 4 to the power and our 64 to the power, what base are we going to put them in? 4. You could do this and switch them into 2's, but that is harder. I can rewrite 64 in terms of 4's. So we're going to have our 4 to the x squared plus 8 equal to 4 cubed to the 2x. So when we're looking at just our exponents, we get x squared plus 8 equals 3 times 2x, or 6x. How do I solve that? How do I get that down to an x equals? Factor it. Which means what do we need to do first? Set it equal to 0. So we're going to set this equal to 0 with our x squared minus 6x plus 8 equal to 0. We can take our shortcut version on this one for our factoring. Pair of numbers that multiplies to be 8 and adds to be negative 6. Negative 2 and negative 4. So our factored form is going to be our x minus 2, x minus 4 equals 0. Remember, we can only take that shortcut when our a value is 1. Stop using that forever. So what are our solutions? What is our answer for x equals? 2 and 4. These are equal in two different places. 4 to the 2 squared plus 8, and 64 to the 2 times 2. And 4 to the 4 squared plus 8, and 64 to the 2 times 4. There's more than one place, and that can happen. These curves cross twice. That's what that's saying. Very similar deal on the right. Rewrite our bases. What base are we going to do? For our 25 to the x squared and 5 to the x plus 6. 5. I can rewrite this as our 5 squared. To the x squared. And our 5 to the x plus 6. We need them to have that same base so that we can look at just the exponents. We don't want to have to do this another way. So we're going to have our 2x squared set equal to our x plus 6. What do we need to do? Factor it, which means I need to get it set equal to. Which of these pieces should we move? The x and the 6. Stop giving yourselves negative a values. It's so much harder to factor. It plays games with our signs. Keep your a value positive. This guy, we want to keep him to be a positive 2. So I'm going to subtract the x and the 6 to get 2x squared minus x minus 6 equals 0. If you subtract the 2x squared, that's fine, but then please factor out a minus 1 because dealing with a negative a value is obnoxious when we're factoring. It plays so many games with your signs. Please don't. So we need to factor this one. We can't take the shortcut on here. Our a times c, 2 times negative 6 gives us negative 12. B is negative 1. What pair of numbers multiplies to make negative 12, adds to make negative 1? Negative 4 and negative 3. I'm going to write down a wrong answer here that I have seen happen lots and lots of times. Please do not tell me that the factored form is x minus 4 and x minus 3. This is wrong. Do not write this down. Do not write this down. Because where's your 2x squared coming from? If I multiplied that back out, I would not get the quadratic we had. This is not our factored form. You cannot take the shortcut if we have an a value. Positive 3. I'm so good at mathing. I got excited to show us the mistake that I made a mistake. Still not the factors. Still wrong. Okay? If you have an a value, that's not 1. Please use a tool. I don't care how you factor. Just that you factor. Use a box. Split the middle. Bottoms up. Whatever you need. Factoring by grouping. Whatever wizardry you choose. Factor. Because what are our factors on this? The right ones. 2x plus 3 and x minus 2. Please don't take the shortcut if we have an a value. I've seen that happening a little too frequently, so I'm just pointing that out. So where are our roots? What are our solutions? X equals what? Negative 3 halves and positive 2. Okay? So, don't take the shortcut if we have an a value that's not 1. Get all the way down to an x equals. Okay? Questions on those guys? Sweet. We got 5 more minutes. We're doing one more. We're going to look at the first one of these. I was going to say, I have them. I'm going to pass them out. This includes all the stories we're going to do tomorrow as well because we're not going to have time for all of them. If you don't want to use it, you don't have to. But I've got them, so. These are we'll finish the other 3 on Monday. So, like, what are we doing tomorrow? Those mom. We'll finish the rest of it. We'll finish the other 3 tomorrow. That's what I meant. My brain is still stuck on the fact that it's Thursday, and my brain's really trying hard to make me believe it's Friday. It feels like a Friday. I want it to be Friday. I'm ready for Friday. My brain's trying real hard to make me believe it's Friday. So we'll finish the other 3 up tomorrow.
Are the other 3
very similar.
Oh.
It's 3, yeah.
Oh, okay.
Yeah, it's 3 on this is 4 of our questions. Just in a row. So we're going to be using our exponential growth. This is still our a b to the x. We just in here have when it's growing by a certain percent. Not necessarily a double or a triple. So it's growing by 2% or decreasing by 2%. So when we're working with these functions, it's looking at our base and how it's going to grow or decay. A lot of times we're used to seeing these formulas, a equals p times 1 plus or minus r to the t. What these letters stand for, p is our principal or our starting amount, just like how a was our starting amount when we didn't have a k there. This is how it's growing or decaying, our 1 plus r. So if we're looking at this town here, we've got this population of Albany, Kentucky, is growing at a rate of 2%, and we have a population of 25,000. So we have a lot of information in that one sentence right here. The fact that it says growing means we're going to use the plus. That's what that one says to me. We're going to have our 1 plus whatever our rate is. What is the rate we're growing at? 2%. So 0.02. Good. We need to make sure we're writing it as a decimal. 0.02. What is our starting population, our starting amount? 25,000. So that is our principal, our starting amount, 25,000. Our exponent is going to be that t. And what the a tells us is the amount of people in town. So if we needed to just write an equation, we'd write it like this. We could simplify. I could simplify my 1 plus 0.02. And then if we're looking to make a prediction, they're going to give us some information. They're either going to give us an amount and we'll have to find t, but that'll be later in the chapter. But right now, we're going to be given a t, or we'll be given t and need to find r. We might have to do that. And we can solve for this information. If I know that the amount of people in town is 25,000 times 1.02, and we're asking about 5 years, how many people are going to be in our town? What do we get when we type that in the calculator?
What do we get?
My calculator got you. Somebody type it in. Otherwise, I'm going to pull my digital one. Schmerp. 27,602.2 blah, blah, blah. Because we're talking about people. Yes, 0.02. Thank you. I was going to say, Can I have 0.02 of people?
No.
That's that you took into your town center and I took a hand. Threw it in town center. I'm pretty sure that's going to affect the number of people in my town. If I start lobbing random limbs into town square. Don't tell me that 0.2 of a person, not even 0.5 of a person counts as a whole person. Children count as whole people. Do not give me decimal points on living creatures. Anything living, we round to real numbers. I don't care if it's fruit flies or people. So 27,602 people. No decimal points on living creatures, no matter our opinions on the living creatures. I don't care if it's elephants or fruit flies or spiders. Living creatures are whole numbers. Money, we're taking 2 decimal places. Living creatures is whole numbers only. We will work more with 5.2 and 5.3 tomorrow. We are not ready for a quiz tomorrow, so that will be pushed to at the very earliest Monday. At the very earliest. We will see how it goes tomorrow. That's where I'm pushing it for now. I reserve the right to push it farther if we need it. But it's definitely not tomorrow.
You laugh like that too.